Hi everyone, I'm Minghui Luo, a PhD student from Paderborn University in Germany. In this talk, I will present our recent approach to modeling Java framework behaviors. Every day in the news, you see software applications compromised because of security vulnerabilities. These vulnerabilities do not just cost reputations of their owners, but also a large amount of money and manpower to fix them. To ensure a high level of security, applications need to be tested, and static analysis is a powerful technique for testing security. However, using static analysis is not common for many applications. Why? These applications are built with frameworks, which provide rich functionality that would take time and effort to create. There is the Android framework for mobile apps, the Spring framework for web apps, and many more. So most applications are not standalone but run within frameworks. The overall program's flow of control is usually dictated not just by the application, but also by the framework too. Given the code of the application, static analysis tools need to create data structures such as call graphs, which give global information about calling relationships in the program. Combined with control flow graphs, these tools can then perform various of data flow analysis, such as tent analysis, to detect vulnerabilities. Since the frameworks are usually very complex, most analysis tools do not analyze them, but rather model them. Usually, some experts study the framework documentation carefully and create a model that, for example, add artificial edges to the call graphs to model the callbacks invoked by the framework. Such modeling is not only tedious, but often incomplete. It can cause analysis to miss critical issues. Often, such carefully crafted model is tailored only for a specific tool and cannot be used by other tools. This comes to our first research question. How can one construct sound call graphs without precise modeling the Java frameworks? Ideally, we would like to have a magic box that automates the process. It should create a model that can be generally used by some important kinds of static analysis tools. Arrows from Ali and Lotak was such an approach for modeling Java libraries. The idea of arrows is to generate a lightweight placeholder library that models the original library based on the separate compilation assumption. Basically, it means the library doesn't know the application when it was compiled, which limits what it can potentially do to the application code. Although arrows creates a model that can be used to construct sound call graphs using popular analysis frameworks such as Sood and Voila, it was not suitable for every client analysis, especially a client analysis that is interprocedural and considers various of sensitivities such as flow sensitivity and fit sensitivity. In our approach, we considered these features and adapted arrows such that it is client analysis aware. We are particularly interested in tent analysis, and we wanted to find out how effective our approach is when applied to a precise client tent analysis. We evaluated our approach with Fraudroid, a precise tent analysis tool for Android applications. We modified Fraudroid to use call graphs constructed with our approach. We run both tools on TentBench. It is a benchmark suite consisting of 39 real-world malware apps with a documented ground truth that can be used to assess a tool's precision and recall. As you can see the recall, our version of Fraudroid detects 11% more problems in TentBench in comparison to the original Fraudroid, even with higher precision. This result shows our approach is very effective. Currently, we are experimenting with the Spring framework and already got some promising results when evaluating micro benchmarks we created. We are looking for more realistic benchmarks. If you know good ones, please let me know. If you are interested in our work, please find more details in the poster session video or contact me directly. Thank you.